Okay, you guys, so you should have out your notebooks, and we're gonna go ahead and we're gonna be talking about light today. Now, you might be like, I don't understand why we're talking about light in chemistry class, but there's a lot of overlap between the way that light works and the way that our electrons behave. So, we're gonna start by talking about light as a wave. So we're gonna go ahead and title this, The Nature of Light as a Wave. Okay, so we're gonna start with this idea that light behaves as both a particle and wave, right? So it's kind of got two properties here that show up. So we're gonna talk about some definitions, and we're gonna use some terms. Hopefully you remember talking about light last year in physics class, but if you don't, that's okay. So the first definition that we're going to cover is electromagnetic radiation. Now, electromagnetic radiation is a form of energy that exhibits wave-like behavior as it travels through space. A form of energy that exhibits wave-like behavior as it travels through space. Okay, so what we can do is we can go ahead and we can draw a picture of a wave. Okay, right? So you have your wave there. My wave's not super pretty, but that's okay. We can label a few things on this, and hopefully you remember this from last year. This is a transverse wave, right? And we can go ahead and first label our wavelength. And wavelength we represent with the symbol lambda, right? And this is the distance between corresponding points on adjacent waves. So if we come up here to our transverse wave, right, here's an example of a crest. There's our next crest. So that is our wavelength, right? Crest to crest, you can also go trough to trough, right? But that's our wavelength. Our other word that we can talk about is frequency. You might have used F to represent that. Here, we use a symbol that looks kind of like a fancy V. Right? And our frequency is the number of waves that pass a given point in a specific time. Now, hopefully from last year, you remember that our unit of frequency is hertz. right? Which is the same as inverse seconds or 1/seconds. So normally our specific time is 1 second, right? So how many waves past that point in 1 second? Okay, so we have two variables here. We have our wavelength and our frequency. What we're gonna do is we're gonna relate these two things, right? So we have a relationship between wavelength and frequency. You should have learned about this relationship last year, but if you didn't, that's okay. Our equation that we use is C is equal to our wavelength multiplied by our frequency, right? C is the speed of light. Some of you may have this number memorized. If you don't, that's totally okay. This is a constant. It's 3.00 times 10 to the 8th meters per second. We also have our wavelength. Right, which we measure in meters. We measure this in meters, and then we have our frequency, which we just went over, that we have in hertz, right? We can check our units here. Meters over seconds is equal to meters over seconds. So that makes sense. Okay, what's important about this? Frequency and wavelength are inversely related. Okay, so if we think about that, hopefully you've learned the word inverse in your math class. But what that means is that as one goes up, the other one has to go down, right? Because they're always going to equal the same number. So let's think about this for instance. If we had an arbitrary number here of like 6, and let's say our wavelength was 2, that would mean our frequency has to be 3. But if our wavelength increased to 3, our frequency would have to decrease to 2, right? So as one goes up, the other one has to come down. Or as the other one goes up, this one has to go down, right? They can't both go up together. They have to do the opposite thing. So we're gonna do one example where we look at this. Our example that we're gonna do is calculate the wavelength in nanometers. The wavelength in nanometers of the red light emitted by a barcode scanner. Right, so this is what they have at the grocery store, right? It scans those barcodes, it looks red. And these barcode scanners have a frequency, of 4.62 times 10 to the 14 hertz. Okay. So once you write down your problem, our goal is going to be to identify what we know and what we're looking for. Okay? They tell us our frequency is equal to 4.62 times 10 to the 14 hertz. We're looking for our wavelength. And we want to know specifically how many nanometers, right? They want that in nanometers. Okay, so we can use our equation where we know our speed of light is 3.00 times 10 to the 8th meters per second. which is equal to our wavelength that we don't know, multiplied by our frequency that we do know. Okay, now it's just a simple plug and chug, right? You plugged in, we got to chug this out. If we're trying to get this variable by itself, and these two things are multiplied, we undo that by dividing. So we're going to divide both sides by 4.62 times 10 to the 14th. Now you might notice, these numbers are both in scientific notation. You have to use parentheses in your calculator. Use parentheses on top, use parentheses on the bottom. If you don't use parentheses, you're going to get a really weird number that's going to be something to like the 22nd value, which is not going to be correct. So if we plug this into a calculator, and you should practice this to make sure you can get the right answer, you should get 6.49 times 10 to the negative 7 meters. Now, hopefully at this point you're like, I think we have one more step, because this is not in our desired units. We need to convert this. So if we take 6.49 times 10 to the negative 7 meters, and we convert, we're going from meters to nanometers. Now this is a little bit of a throwback to when we learned those prefixes. Hopefully nano, that N makes you think of 9. It's a very similar prefix. And in 1 nanometer, there is 1 times 10 to the negative 9 meters, which means, once again, use parentheses when you plug in. This is 649 nanometers. There's your final answer. You can box it, you can sig fig it, you get 3, and you should be good to go. Okay, so this is all of our nature of light as a wave, but light also can behave the other way, right? We said at the beginning that light acts as a wave, but it also acts as a particle. So let's go ahead and think about that. So if we have the nature of light as a particle. Nature of light as a particle. Okay, we're going to once again go through some definitions that are more specific to our particle type behavior. Okay, the first thing that we're going to talk about is what's called the photoelectric effect. Now, the photoelectric effect is essentially this. This is when we have an emission of electrons. Emission of electrons from a metal when light shines upon that metal. We'll talk more about this next class. But this is a natural phenomena that we see a lot, but only works with metals. Then we're going to talk about this idea of a quantum of energy. A quantum of energy is the minimum quantity of energy that can be gained or lost by an atom. And the the last thing we're going to talk about is a photon. Now, a photon is a particle of light having zero mass. Particle of light having no mass, right? Zero mass. And carrying a quantum of energy. Okay, right? So this photon here, right? This is our particle of light, right? Light's acting as a particle, and it's going to have no mass, but it's carrying the minimum amount of energy that can be gained or lost by an atom. So however much your atom can gain or lose, that's how much your photon is carrying. So what we can do is we can actually calculate the energy of a single photon. Which is pretty cool. So here's the equation that we use. We use the equation E equals H times our funky looking V, right? Energy is the E. Hopefully you remember we measure energy in joules. This is our frequency, which we still measure in hertz. And then we have H. This is Planck's constant, right? So this is a value that stays constant. And its value is 6.626 times 10 to the negative 34 joules per second. Sorry, joules times seconds. Right? So we can check our units again. Joules times seconds. Hertz has seconds on the bottom. That will cancel out and you're just left with joules. But we can also think back to our last equation, right? Where we know that our wavelength times our frequency is equal to the speed of light. Now, if we divided both sides by wavelength, right, to get frequency on its own, we would find that our frequency is equal to the speed of light divided by wavelength. So we could also rewrite this equation as energy is equal to Planck's constant multiplied by the speed of light divided by wavelength. So we have two equations that we can use to calculate energy. So we're going to do an example. Our example that we're going to look at is determine the energy in joules of a photon whose frequency is 3.55 times 10 to the 17 hertz. Okay, so we can look at what we're given. We're looking for energy, some value in joules. We're given that our frequency is equal to 3.55 times 10 to the 17 hertz. So we pick which equation we want to use. This equation has both energy and frequency in it, so it is a plug and chug. So we can plug in Planck's constant. We're going to multiply that by our frequency. So go ahead and plug that into a calculator, and once you do that, you should get a value of 2.35223 times 10 to the negative 16th joules. If you sig fig that, you should get 2.35 times 10 to the negative 16 joules. And that is your final answer. Okay, so now that we have talked about light and how it can act as both a particle and a wave, we're going to go ahead and talk about how that relates to electrons. So we're specifically going to be talking about electrons according to a guy named Bohr. Now, you may have heard of Bohr before because he created the Bohr model, which is something that you probably will recognize, right? But it's where you have your nucleus in the middle and you draw rings of electrons orbiting around it, right? We drew a couple right at the beginning of this unit when we were looking at what was in an atom. So according to Bohr, there's two terms that we need to think about. We have the ground state of an atom, and we have the excited state of an atom. So in the ground state, this is the lowest energy state of an atom. Which means our excited state is a state in which the atom, or any atom, the state in which an atom has a higher potential energy than it has in its ground state. Okay, right? So ground state is kind of like the base. It's where it's always at, lowest energy state. And then we can go to an excited state where we have a higher potential energy, right? And it's always just compared to that ground state. So we're going to talk about an experiment that Bohr did to be able to figure this out. But essentially, he looked specifically at hydrogen. So Bohr took a sample of hydrogen, right? And I'm just going to draw a little picture, kind of showcase this, right? So we have a sample of hydrogen atoms. And we're just going to show these as little dots, right? This is our sample of hydrogen atoms. And what he did is he added energy. So we add energy to this sample of hydrogen atoms, and what happens is that some of those hydrogen atoms absorbed the energy. Right? So they absorbed the energy, and as a result, they entered that excited state. So Bohr was able to get the sample of hydrogen atoms out of the ground state and into the excited state by adding energy. So then what happened? Right, we have our sample. And a few of these atoms, right? They're excited. This is how I'm going to show they're in their excited state. But do we think we want to stay at our our excited state forever? Probably not, right? This isn't a long-term thing. So what happens is these atoms release a photon, which should ring a bell because we just talked about what a photon is, right? That's a particle of light having no mass and carrying a quantum of energy. Right? So then we can say the excited atoms emit photons of light and return to the ground state. Our excited atoms emit photons of light and return to the ground state. Right, so then our sample goes back to how it looked before, right? So Bohr came up with his idea of how electrons are located in an atom just based on this experiment, right? He figured that what happens is we have electrons that are located in orbits, right? Circles around the nucleus, and when they get excited, they can go from one orbit to the next, right? They move away from the nucleus, and then when they release that photon, they fall from the outer orbital back into their original position. So we can go ahead and look at this, right? So there's a couple different ways we can think about this. We can think about this from an energy perspective, right? So if we have a graph where we're looking at energy, you have your excited electron, and then you have your original state, right? And the difference between those two things is our photon. Right? So that's our big deal, right? We're adding energy, but you're losing energy because you have to have the conservation here. So Bohr examined this type of, we call this an emission spectra, right, of hydrogen, and he created his model based on that. Hydrogen, a model based on that. He thought electrons had restricted circular orbits. right? And at this point in time, we already knew there was a nucleus, so you thought those went around the nucleus. Now the good news is, and the reason that this worked, is because this fit hydrogen perfectly in terms of the data, right? This fit hydrogen's data perfectly. But it didn't fit for other elements. Now, we still sometimes use this Bohr model as it's a pretty easy way to showcase certain things, but it doesn't always work, right? So what this looked like, right, is you have your nucleus in the middle, and we have rings that orbit, right? And we say that these are different energy levels, right? So we say like first energy level, second energy level, third energy level, right? And we can always still remember that we're connecting this to what we just learned about light as a particle, right? So the energy of those photons that is emitted is equal to Planck's constant times our frequency, right? This is for a photon is emitted with energy defined by that. So what they found is that, right, let's say that an electron has this ground state of 2, right? It's in that second ring. Well, it could pop out to the third ring, but it could also pop out to the fourth ring or the fifth ring or the sixth ring, right? And wherever it's popping out to, that gives a different amount of energy being released, right? So we can draw a picture, right, of, let's say, we have our ground state of 2. And sometimes it'll drop from 3 to 2, sometimes 4 to 2, sometimes 5 to 2, and sometimes 6 to 2, right? Depending on how much energy, we're able to absorb, this will depend on how much energy can be released. So if something makes this jump, right, just jumps up one level from our second level to our third level, when we release that light, it has a wavelength of 656 nanometers, right? So it's red light. If we go from 4 to 2, we release a wavelength of 486 nanometers. So that's a green light. If we go from 5 to 2, we release with a wavelength of 434 nanometers, which is blue light. And if we go from 6 to 2, we release with a wavelength of 410 nanometers, which is purple light, right? So depending, right, our energy can be related to colors, and also it's related to how much energy goes in, right? Different wavelength means different frequency, which means different energy. right? As these wavelengths are going down, our frequencies are getting higher, therefore our energy is higher. So a bigger jump means more energy is released. Okay, we can draw one last picture to explain this, and then we're gonna call it a day, and you guys can work on practicing these calculations with light and photons and all of those wonderful things. So what these spectra look like that Bohr was looking at is they were an energy spectra, right? So we have energy, and we have our ground state, and then we have our different levels. And these are exciting states, right? In this case, we have 4 excited states. So if we have an electron that pops up to the first one, when it goes back to the ground state, if we're looking at the same kind of thing that we were over here, this would release a red photon, right? This would release a red particle of light because this is its wavelength, right? If we go to our second one, it's gonna release a green particle of light, right? Because it has a lower wavelength. More energy is being released. If we go to our third, it's gonna release that blue particle of light, that blue photon. And if we go to our fourth excited state, it's gonna release that purple. Now, for each individual element on our periodic table, there's only certain excited states that are allowed, right? So we say only certain energy levels are allowed. And the word that we use to explain this is we say that our energy levels are quantized. Right? There's only certain states that we're allowed to go to. And every atom is quantized. Right? So sometimes each of our individual elements have different levels that they're allowed to go to, which is how Bohr was able to look at the different spectra, right? Last thing that you should note about this, right? The further that electron falls, the higher energy photon it gives off. The further an electron falls, the higher energy photon it gives off. Right? We can think back to our electromagnetic spectrum, right? When we go through the visible light spectrum, purple, higher energy than red. Okay, you guys, so you can go ahead and find your homework up front, right? It's some calculations with light. So go ahead and work on that, and I will see you next class. Okay, so, right, we have talked about how Bohr used his model to look at different spectra of a variety of elements, right? The first one that he investigated was hydrogen. So we saw that we have these different levels, right, that electrons can be excited to, and as a result, they would release a different color photon. So we're gonna look at 3 different elements and see what colors of light they actually produce, right? So the first one that we're gonna look at is hydrogen. Now what this is this is a really high voltage Tesla coil technically, And so what it does is we have a amount of hydrogen in here, and you're gonna be able to see that electricity travel through the hydrogen, and it's going to release a color. So if we turn this on, we see that our hydrogen spectra shows purple. So this is a really high energy thing. I can move it closer so you can see it. Right? This bright purple color. So then we can go ahead and turn that off, and we can compare that to some of our other spectra. So if we remove this, we can compare this to a different gas. So the next one we're going to look at is helium. So in comparison to hydrogen, when we put helium in here, it's a much brighter color. And we can relook at these next week when we're all in class together. But it's more of like an orangish, white, yellowy light. And the last one that we can compare this to is we are going to look at neon. Neon's the last one that we're going to look at. And neon creates this really cool red, right? Similar to what you hear about like a neon sign. Looks pretty cool. Okay, so this all goes back to this idea that different elements are quantized, right? We have 3 different things here, and instead of all showing the same color, they show different ones because their electrons are being excited to different levels and releasing different amounts of energy when they go from that excited state back to their ground state, right? So we'll continue investigating this next week when we do a lab specifically looking at some different chemicals, and we'll be doing flame tests where we can see the same type of colors in their emission spectra. So this is a really cool way for us to be able to identify an unknown thing, right? We can look at what their emission spectra is and figure out what our unknown element would be. A couple reminders, you guys, please make sure to do that light homework that's up front. Make sure that you study for your quiz next week. It's going to be on atoms, ions, and isotopes. And please send me any emails if you have questions. I hope that you guys have a great weekend, and I'll see you next week